So my blipper I think needs more juice. All right. Unit 3, I told you, and I'm glad you're really here today. You probably want to listen up. This is actually in my classes in general chemistry. Sometimes students don't listen to the first lecture. They listen to maybe the 4th lecture, and then they don't know where they're at because they didn't listen to the first lecture on the topic. I'm just throwing that out there. So I kind of set the stage for some things called thermodynamics. As I mentioned, this is a topic that some of you have not covered yet in high school. We'll get to it. Thermodynamics in general is the study of something we can't see. It's the study of, we know it's there, the study of the flow of energy. And actually, we're going to focus on, when we get going here, a lot of the flow of thermal energy, only one type of energy, right? So, energy, by definition, would be, energy is the ability or potential to do work, okay? And, or, if you're not going to do work, you're going to transfer heat. You're going to give up heat, bring in heat. You're going to do work, work's going to be done on you. So energy is the ability to do work and or transfer heat. And some of these terms might sound kind of physics-ish, and that's not an accident. There's an intersection of chemistry and physics. So we can broadly talk about 2 types of energy. We can talk about potential energy, sometimes called stored energy, sometimes called the energy of position. And or we can talk about kinetic energy. Kinetic energy, if you take in physics, is energy associated with motion. So kinetic energy, energy associated with motion, potential energy is stored energy. And there's all sorts of different ways to think about this. In real life, actually, potential energy and kinetic energy sometimes kind of go back and forth. One can be converted into the other. So here we see a dam. So kinetic energy is energy associated with motion. So you see the motion of the water going over the waterfall. And actually, the next slide says that this dam then, that water going over the waterfall, that's kinetic energy. And of course, we know that objects fall faster and faster towards the earth, and they accelerate. And so down here is a turbine, so we can get that moving water to move a turbine, and that turbine then can actually take that kinetic energy and turn it into electricity. So it's all good, right? Energy can be converted from one form to another. Potential energy, honestly, is energy associated with position. So up here, when the water is just barely, well, I think it's probably flowing pretty good. But up here, we say the water with regard to falling due to the Earth's atmosphere has less potential energy, has the most potential energy. And down here, it has least potential energy, more kinetic energy. So at the top, less kinetic energy, more potential energy. At the bottom, less potential energy, more kinetic energy. So here's a picture of the dam. Things to scale, like big things like that, sometimes just give me some sort of vertigo. I don't know about you, but so that's energy. So one of the things we need to get under our belts is how are we going to quantify energy? What sort of units are we going to use for energy? So of course we have the English and the metric, right? I think of calories as being the English, and you know, I'm kind of a picture person. So I would think of 1 gram of water. So actually 1 gram of water is going to be 1 cubic centimeter of water. So here's a little box that's 1 centimeter on all sides, and that's going to be my 1 gram H2O. We can see what this is saying. Actually, and you can see it's historically. So at one time it was defined, we used calories in this way. But if we take 1 gram of water, we can zap it with energy. Okay, specifically how much energy? 1 calorie. And I'm going to use a lowercase. You're going to see that there's another type of calorie with a capital C coming up. Lowercase calorie. And that is going to make the temperature rise, because zapping it with energy should make the temperature rise. If you're talking about temperature rising or falling, go from 14 degrees Celsius to 14.5 to 15.5 degrees Celsius. So, i.e., it'll go up 1 degrees Celsius. A little experiment. Yes, ma'am.
When you necessarily start from 14 degrees and a half, or can you lift it up from 0 to 1?
There will be a slight difference, as I understand, I think, if I'm understanding this right, depending upon which temperature range, but not much of a difference. So I think for our purposes, I could take another chunk of water that's 1 gram, and I could go from 20 to 21 degrees Celsius. And that actually would correspond to 1 calorie. Yeah, for our purposes. But that's kind of historic. So now we use joules, and I kind of think of calories as English and joules as metric. I don't know if that's entirely right. But the energy of joules, then now calories is related to joules. And I'm going to put a little star next to this. So 1 calorie is exactly equal to 4.18 J for joules. What do my stars mean? What do you think? You have to memorize it. Yep. That's independent of water. That's everything. That's just energy units. Yeah. 4.184. Sorry, my bad. Okay, very good. So I mentioned that actually this is case sensitive. I said a lowercase. This actually calorie is what we call thermodynamic calorie. But if you flip a candy bar over, actually it's going to give you food calories. And so the way we distinguish between the two is we use food calories, dietary calories. We use a capital C for dietary calories, and we'll use a lowercase c for thermodynamic calories. And I have on my next slide with the relation to, well, I already have it here. They're off by a factor of 1,000. So dietary calorie is actually 1,030. Yeah. So 1 big C is equal to 1,000 little c's. Okay? I like that. So a joule, so if by definition now 1 calorie is equal to 4.184 joules, we need to have a definition for what a joule is. And it kind of goes back a little bit to the idea of kinetic energy. This is also a picture. Got a lot of pictures here. Okay, I have a little box here. Like it says, so I have a 2 kilogram mass, 2 kilogram mass. That's how massive my block is. And it's moving at a velocity, this will make sense why I need to do this, velocity of 1 meter per second. Okay, you got that? That's my scenario. And I'm going to show you how that works in. That block right there, we say, has a kinetic energy of 1 joule. Okay? So KE is equal to 1 joule in this case. Exactly. If you want to break a joule down into littler units, behind the scenes, a joule is really a kilogram meter squared per second squared. Again, that gets kind of into kind of the physics side of that. We won't need to be doing that. Notice that the abbreviation for joule is a capital J. Okay. This actually is why this works like this. Some of you guys may have learned that the kinetic energy of an object, if you know its velocity and its mass, kinetic energy is 1/2 mv squared. So let's return to our block. We got 1/2, the mass we said is 2 kilograms. 2 kilograms, and, sorry, velocity we said is 1 meter per second. Let's do it this way. 1 meter per second, and we're going to square that. Okay, so this 1/2 and 2, they cancel, they give you 1. Of course, the number of 1 squared is 1, and that gives you 1 kilogram meters squared per second squared, which is 1 joule. I'm just saying that's where it all comes from. Okay. Okay. K is equal to 1/2 mv squared. Right. That's where the joule comes from. So know these relationships. You can put a star on this one, which actually has the star I told you about. The relationship between a joule and a thermodynamic calorie is this. 1 calorie is exactly equal to 4.184 joules. And then we talked about there's 2 types of calories. That there's the thermodynamic calories, the lowercase c, and then there's the dietary calories, the capital C. So somewhere in the back of wherever you put things, know that. All right. So the term thermal energy. So thermal energy and heat are synonyms, synonymous. Okay, thermal energy and heat are synonyms. Here in a minute, I'm going to throw in a third term, temperature, not a synonym. I'm saying that right yet. Not it. Okay. So, all matter, I think we talked about this clear back in Unit 1 in here, all matter is in motion. There's different types of motion depending upon kind of sort of the physical phase of the motion. There's the vibrational, rotational, and what we say translational. So that matter actually, that motion of that matter is the kinetic energy of it. Okay, so all matter is in constant motion, so all matter has a certain amount of kinetic energy. I think we've already talked about a little bit about the different temperature scales maybe, and if you go ahead and cool down matter, I'll go ahead and throw it out there. If you cool down matter, do the particles, some people think they move faster. Some people think they move slower. Exactly. So if the matter moves slower, basically your velocity term is getting less, so it has less kinetic energy. Exactly. You got it. So thermal energy is what we say the motion associated with the movement of the matter, and it's one type of kinetic energy. Okay. So yeah. I'm going to show you one of my favorite little videos coming up, and it's where I show the 3 physical phases. We have solid, liquid, and gas. So I think we talked about this in the first year material, solid, liquid, and gas. How many people think solid has the most motion? How many people think gas has the most motion? You are very right. Very right. Okay. Okay. So here's that little video I was telling you about. I hate to think maybe some of you guys can't see colors, but on the left we have red, on the right we have blue. Now, can you kind of see what's different other than the color about these? I think they're similar amounts.
The area is covering.
The area is covering, I agree. Yeah. The area is covering, and this one looks a little bit bigger too, doesn't it? Yeah. I think it's got more volume, and we know that matter swells, and these have more movement, as shown by kind of what would you say? Yeah, the rings are around it. This is showing more motion. Exactly. And it's exactly what you guys told me, that when you heat something up, it has more motion. Yeah. So hold that thought. Okay, so I brought this little IR gun in here. It is just so fun. I'm telling you, we have, this says like 70.7 is the temperature of that wall, the temperature of my forehead, 92.8, right? These are really handy when you're trying to find drafts in your house. So keep an eye out for that. Drafts in your house. Like if you know a room is cold, but you don't know where the insulation is bad, like, oh, I have to find the cold spot. They're also great for finding ghosts. I'm just kidding, sort of. Anyway. Yeah, I know.
Because of thermal energy change is what it is.
I know. I'm not making fun of anybody, because I find it fascinating. So anyway, where were we at? So temperature, I can do this to find the temperature of anything. You guys have used it to find the temperature of something. All temperature is doing is finding basically how fast those molecules are moving. Okay, so it's a measure of how fast those molecules are moving. As this wall cools down, they move slower. As this wall heats up, hopefully what will heat up to the point to liquefy the wall, okay, but they go faster. So temperature is an indication of how fast they're going. Temperature also can give us direction as to which direction the thermal energy is going to go, okay, and I have some, basically it moves from hot to cold. I'm going to try to convince you of that. When it's cold outside and we open the door to the outside, let the dogs in or out, it feels like cold air comes in, but the way the molecules are going is the hot air inside has more energy and it's going to force its way out. And some cold's going to come in too. But the aggressive stuff's going to be the stuff with the most kinetic energy, basically. So it shows you which direction thermal energy is going to flow. So thermal energy and heat. Thermal energy and heat. When we get going, we're going to actually sort of be able to look at an object and have a sense for how much thermal energy or heat it has. Okay? So we can measure the temperature, but the temperature is just how fast the molecules are moving. Thermal energy and or heat is how much thermal energy it contains. So those are two different things. So heat and thermal energy can be used interchangeably. Temperature cannot. Okay, this is just a snapshot of whatever. I can take a snapshot of this. Okay, 73.4, right? That's just the temperature. That's not the thermal energy. If it's thermal energy, I'd have to say 73.4 joules. Just the thermal energy. 73.4 degrees Fahrenheit. So temperature. Temperature is important, though. We've talked about two types of properties, intensive and extensive, yin and yang. What does it mean? Temperature is an intensive property. What does that mean? Independent of amount. Very good. Independent of amount. So, you know, I could do this like that block right there, and you look at 71.0, or I could talk about, you know, this whole set of blocks, like 71.0. Okay? It's independent of amount. Okay? All right. So, when we get going after break, so we don't have class on Friday, right? No class on Friday for any SEC classes. But when we come back, the next week, we're going to be talking about like how much thermal energy an object has in general. Now, we're going to need to know its temperature. The other thing is we're going to need to know its mass. And the third thing we're going to look up on a table or whatever, we're going to need to know a property called specific heat of the object. So 3 things. Its temperature, its mass, look up on a table, its specific heat. Okay. So here in a minute now, I'm going to show you a few little slides that go back to your opening from your warm house on a cold day. What direction does heat flow? And I like to think of it, I hadn't thought of it until just kind of when I was working with you guys just now. If we think of the hot, whatever's hot is being aggressive because it's got more motion, more kinetic energy. It's like if you have a friend that's not very awake or whatever, not very into something, you got to bump that friend until that friend gets going, okay? That's how I think of it. So this video kind of shows you left and the cold on the right, red and blue respectively. And we're going to go ahead and let the two meet. So now the two boxes have come in contact. Now there's different ways for thermal energy to transfer. This would just be by what we call conduction. So just kind of bouncing against a common wall. And then just like we saw in the video, it all kind of is purple in the end. Starts out blue-red, kind of swapping. Okay. So transfer of thermal energy, thermodynamics. So when we start working problems, you're going to hear the word, I don't think we use it here yet, but equilibrium. In this scenario, the equilibrium is the last one where they both have equal temperatures. And when we start doing problems, you're going to see that you're going to admit something that's hot into something that's cold, give it a little bit of time, make sure your container's insulated, and they're both going to, the one that's hot is going to impart energy to the one that's cold. Okay, so that's kind of the crux of some of the problems we'll be doing in here. All right. So a little bit about temperature scales in general. For me, I look at the Fahrenheit temperature scale as to, I'm looking at my European friends. If you're wondering, you're fine. If you're wondering like what temperature it is outside, I'm looking Fahrenheit. Do you guys look at the Celsius temperature more?
Yeah, I still do. Actually when it's hot, when in the summer I look at Fahrenheit, and winter I look at Celsius because it's easier. I don't know.
Interesting.
I got used to 72 is that perfect temperature, and then I go off of that, but 0, but when it's cold, I go off Celsius.
Same kind of?
I couldn't believe somebody told me that last winter here it was 0 Fahrenheit.
Yeah,
And I had to argue with them, no Celsius, right? And then no Fahrenheit.
We're weird. Everybody else does metric. We do.
Yeah.
I think there's like another country somewhere
There's, like,
close to
2.
Africa that does it.
Well, yeah, Celsius is metric-ish, but honestly, there's that third temperature scale, which is Kelvin, which is even more, and I'm going to compare the 3 temperature scales coming up, which is even...
It's weird, you can't reach an absolute 0 on Kelvin. People have tried.
Right.
They're getting
They're getting very close, but it's taking them how long to get close?
Yeah.
It's chilly.
So to compare the two, with Kelvin aside, we can actually kind of look at the transition temperatures of water. So you guys would tell me water transitions from a solid to a liquid, or liquid to solid, about 32 Fahrenheit, which is 0 Celsius, which is kind of a nice number. And then it boils at 100 Celsius, transitions from a liquid to a gas at 100 Celsius. And for us, what it is, it might be on the slide. For Fahrenheit, it's 212, yeah, which is kind of weird. Okay. So this thermometer is actually trying to kind of show you those important transition temperatures. Here's another, it's not a transition temperature of water, but this is kind of fun. If you do the math, I know you guys already knew this, it's like one of those trivia things. If you do the math on the Celsius and Fahrenheit temperature scales, -40 is the same.
Whoa.
Isn't that cool?
Huh.
Now, -40 Fahrenheit's really cold. -40 Celsius would be really cold. So I'll throw in the Kelvin temperature scale, and again, I'm going to kind of compare these 3 temperature scales coming up. But the Kelvin's got a lot going for it. The biggest thing the Kelvin has going for it, and we'll talk about it here in a minute, is that 0 Kelvin actually means, I heard somebody say absolute 0. 0 Kelvin actually really means something. The cool thing about the Celsius, the metric temperature scale, is they have the same unit, so they're lock and step. I can kind of look at these two for comparison. So at 0 Celsius, you're at 273.15 Kelvin. Notice if I go down 40 units on the Celsius scale, I go down 40 units on the Kelvin scale too. So 273.15 minus 40 is 233.15. So I'm kind of showing you that they go step and step. Fahrenheit's kind of its own little creature. All right, so again, just kind of comparing the 3 different temperature scales. Side by side by side. Okay, so I'm going to walk you through the conversions from Fahrenheit to Celsius and Celsius to Fahrenheit. And I've never put these on a test, but I guess I would reserve the right to do it. You never know if I get wild hair. There's a formula I'm going to show you here in a minute, how to go back and forth between the two. Okay. But to go back and forth between the Celsius and Fahrenheit scale, you can't do it using a ratio, the factor label method, because they are of the type of a scale in general called an interval level. And I'll show you what that looks like. Kelvin is a ratio level. So here's what I mean. Like, what do you mean by levels? So we do it all the time, but we don't even know it. So for instance, the cheapest or the least sophisticated, the lowest level of measurement would just be nominal, okay? In nominal, I could go ahead in here and I could break up blondes and brunettes and redheads, okay? That's just chunking you, okay? I'm not saying anybody's smarter or anybody's more talented or anybody is better house cleaner, okay? With no numeric ranking, okay? Then there is the ordinal, okay? And I'm not going to do this, but I could go ahead and break you up by the color of your hair, and then I could go ahead and say, I would imply a ranking there. Notice the color of your hair is non-numeric. The color of your hair is non-numeric, right? But I could go ahead and imply some sort of ranking, which would be really dumb of me. Really dumb of anybody. Okay, so those are nominal and ordinal. Now, interval, we have numbers involved. Interval, we have numbers involved. And in the interval means that actually you can say, for instance, I told you that the temperature scales of Celsius and Fahrenheit were interval. You know, you guys would tell me that a 50-degree day, 50-degree Fahrenheit day is cooler than an 85-degree Fahrenheit day. They have a number, you can rank them, right? But with this one, interval, it has numbers, but the 0 doesn't mean anything. So if we stick with the temperature scales of Celsius and Fahrenheit, 0 Fahrenheit doesn't mean anything. Why do I say that? Well, I can have a negative Fahrenheit. I can have negative 10 Fahrenheit. I can negative 30 Fahrenheit. 0 doesn't mean anything. 0 Celsius is the same thing. I can go into the negative area. I got numbers. I can give relative to each other. But 0 doesn't mean absence, in this case, absence of molecular motion, absence of thermal energy. On the third temperature scale, the Kelvin temperature scale, that the 0 does mean something. You guys told me 0 Kelvin means absolute 0, and it's not been attained, it's just been approached. 0 Kelvin means all molecular motion stops. So 0 Kelvin actually means something. 0 Celsius and 0 Fahrenheit, not so much. Okay? It's just on a continuum. So on the Celsius scale, maybe some of you guys got this, have committed this to memory, but if this is my Kelvin temperature scale, and this is my Celsius temperature scale, do you guys remember what is it down here, absolute 0 on the Celsius scale?
273?
Yep, negative 273.15 degrees Celsius, equal to 0 Kelvin.
Yeah,
So.
0 in the Celsius system means that water freezes.
Mhm.
Isn't that something?
It is something, but it's not the absence of something. So you're right, there is a significance.
But there's still movement.
Yeah, there's still movement. It's not the absence of the thing you're
talking
measuring.
in terms of movement and
Mhm.
energy.
Yeah, and kind of along those lines, if you say something is, let's go with length. If you say it's 2.5 centimeters, 2.52 centimeters, or if you say it's 0.76 centimeters, okay? If you say it's 0 centimeters, it means it has no length. Yeah, and you can do that with everything. We have 0 mass. 0 means absence of whatever that quantity is. In this case, it would be thermal energy, absence of motion, I guess it'd be. Yep. So a true 0 implies that you don't have, it's the absence of that quantity that you're trying to measure. Okay. So interval versus ratio, they both involve numbers. Ratio means 0 really means something. Well, absence of that quantity. So if you have a ratio level scale, then you can actually use factor label just to kind of knock it out and go back and forth between quantities. So this actually is kind of building up to the formula to go back and forth between the Celsius and the Kelvin scale. Here we have just 2 temperatures. This would be the temperature at which water freezes. This would be the temperature at which water boils on the Celsius scale, 0 and 100. Over there along the y-axis, we have the corresponding temperatures in Fahrenheit. So we can use the slope of that curve. You know, we only need two points to make a straight line. You can use the slope of that straight line to come up with a formula. All right, so here are the 2 formulas. And I'm not sure whether to put a star on this one or not. I'll consult with my colleague, but I don't think it's a very important skill to learn. But the way you read this is, if you are trying to get to degrees Fahrenheit from degrees Celsius, use the top one. If you're trying to get to degrees Celsius from degrees Fahrenheit, use the second one. You just kind of plug and chug. And actually, right here is a place, if you Google it, you can come up with a conversion thing online. So, of course, 0 Celsius is 32 Fahrenheit. 100 Celsius is 212 Fahrenheit. And what's that? Yeah, I know, right? 40 Celsius, that'd be very hot. I mentioned the negative 40. I played around this at my office. So -40, they're the same number. Kind of fun. Let's see, how about -300? Oh, what's wrong with -300 Celsius? It can't be obtained. Exactly. I went to, and I hope they fixed it by now, but I don't know. But the planetarium there in Chicago, and they had some really cool exhibits, awesome exhibits. And one of the things they did was for each planet they had a plaque that gave some good information about it. And at the time I went, they had like a bar to show different temperatures, and they showed on the bar how cold or hot that planet was. And it went down to -300 Celsius. I was like, oh, you fools.
How high can that thing go, I wonder?
What's that?
How high can it calculate?
I don't know.
Let's put like 9999. Wow. I wonder how accurate that is, though.
I don't know. It's just plugging in this formula down here.
Yeah.
Oh, goodness. I agree. So then here are my examples. I don't know if you want to jot these down in your notes. So if we have the Fahrenheit temperature we have the Celsius temperature trying to get to Fahrenheit, this is how we would do it. We would, if 25 Celsius is what we know, we take 1.8 times 25 plus 32. 1.8 times 25 plus 32. And so you're looking at 25 Celsius would be a nice 77 degrees Fahrenheit. When you go into the ER, it's kind of vivid, and they'll have these conversion charts. So they'll take your temperature and I don't know why they'll convert it, but nurses, all that stuff. Okay, so here's the other one. This one, actually, you're trying to go from Fahrenheit to Celsius, and it looks like this. So your Celsius temperature, in this case, our Fahrenheit temperature is 98.6. Right? 98.6, and from that you subtract 32 units, and then you divide by 1.8. 98.6 minus 32 divided by 1.8, and you're looking at 37.0 degrees Celsius. Isn't that normal body temperature? I think I could go. So, 37.
36.6 is actually the perfect body temperature.
Oh, okay, 36.6.
Yeah.
I defer. So as kind of obscure as I feel like this, maybe this would be, the next slide you might want to put coming in here in a minute, you might want to put a star on it. Because the last conversion I want to show you in this part is going back and forth between Celsius and Kelvin. Yes. So that's going to be something you're going to sometimes need to do in this class. So this is why the Kelvin temperature scale is so darn awesome. I almost said cool, but awesome. Okay, it is at the ratio level of measurement because 0 Kelvin actually means the absence of thermal energy. So that's consistent with if it has no thermal energy, it has no motion. And then it breaks the law of one of the tenets of matter, is all matter has motion. How do you handle that? Okay, so 0 Kelvin is actually the lowest temperature that can ever be attained, but has not been obtained that I know of to date.
That can be obtained on Earth or in space?
Anywhere, because in our universe, now we could go to, if you think of there's other universes out there that might have different rules, but our universe has that rule that all matter has motion. And if the motion stops, you're at 0 Kelvin, then it's no longer matter. It becomes very weird. So, and so in our universe. Years ago, I remember there was an article out there, oh my gosh, they got colder than 0 Kelvin. And if you track it down, basically they used kind of a distribution, like a bell curve, and they're like, based upon this, we've got some temperatures that are colder. All right, so this one, put a star on. Okay, so this one actually, when we're working problems in thermodynamics, and when we're working gas law problems, or gas problems, which actually is unit 5 in this class, you might be given a Celsius temperature and need to convert it to Kelvin, or you might be given a Kelvin temperature and need to convert it to Celsius. If you're like me, I hate memorizing things. So I always remember this 273.15 that you see up here. And then I remember, how would you offset it? So if you have the Celsius temperature, you're going to add 273.15. Case in point, if I go up here, remember this is Celsius and this is Kelvin. I know this is a little messy, okay? But I go to 0 degrees Celsius, that actually corresponds to 273.15 Kelvin. Okay, and that's how that works. If I have the Kelvin temperature and I want to get to Celsius, I have to subtract 273.15. So if I picture the scales, I can come up with whether I add or subtract. Okay, that's all I got, Mon. So I know there's like a part that's due Monday, and when I looked at it, I think it should kind of track pretty good with this part. So it's due Monday evening, so if there are any that you should be able to after you take your test. And so yeah, I encourage you for Unit 3. Let me know if you have any questions. I've gone ahead and revealed the OpenStax homework that I've done for past semesters, along with my workout solution. So if the Alta is like not your thing, you're just gonna have to eat those points, feel free to look at the OpenStax.
That's the thing. Alta doesn't allow us to eat those points because if we don't do it, it drops our grade really bad.
I don't think it drops it really bad because you're not working on it.
Yeah, it does.
But if you
It's over 10% of your overall grade.
if you do it, it doesn't bring your grade up. But if you don't do it, it drops it.
Well,
More than you
It's
think.
kind of
it should.
strange, yeah. Pay
Look at
attention
that.
where you do all the homework and then it doesn't increase your overall grade even like after a while. Maybe it does it at